Good evening and welcome to this video for nuclear reactions, and this will be a part 1 of a two-part series. Nuclear reaction is part of the internal standard for modern physics, but this is also tested on the scholarship examination at the end of the year. So the first thing we're going to know about is nuclear reactions. Okay, so nuclear reactions includes a transformation of one nucleus to another. So in all nuclear reactions, conservation laws are required to be followed, so that is conservation of momentum. But however, instead of conservation of mass and conservation of energy by itself, Einstein states that mass and energy are equivalent, therefore we have a conservation of mass energy. And third of all is conservation of charge. So there are quite a few types of nuclear reactions, but for level 3 standards, we're going to be focusing on nuclear fission, nuclear fusion, and nuclear decay. Right, so starting off, we're going to be looking at the nucleus of an atom. So the nucleus of an atom contains both protons and neutrons. We should know about this from our chemistry. However, we know that since like charges repel, therefore the protons should theoretically repel each other by electrostatic repulsion force. So therefore, according to this, that the nucleus should disintegrate. So the protons should repel each other, so that all of the protons will be separated from each other and the nucleus will disintegrate. However, this actually doesn't happen because we have our nucleus is the nucleus and the protons and the neutrons, they're very tightly bound together, so obviously they're not being repelled. So this is due to the presence of the strong nuclear force, which is the strong binding force between the protons and neutrons. So there's a very strong binding force between the protons and the neutrons. However, this binding force is very significant at very small distances. So at very small distances, this force will overcome the electrostatic repulsion. Therefore, the nucleus will be held together because the nuclear binding force is bigger than the electrostatic repulsion. However, this is only significant at very small distances. So bracket here we have it's only about approximation is 1 times 10 to the power negative 15 meters. So that's very small distances there. Alright, so here's a graph of the strong nuclear force with distance. As you can see, when it's above the x-axis, it's actually a repulsion force, but when that small distance where it's below the x-axis, that is when it's a attraction force. Okay, so it's a very strong attraction force that can overcome the electrostatic repulsion. Alright, so a side note, okay, so in the nucleus we have the protons and the neutrons, so therefore we refer to the protons and the neutrons as a nucleon. So a nucleon can either be a proton or a neutron. So a nucleon is a proton or a neutron inside the nucleus. So the nucleus can undergo nucleus reactions, and the main purpose of the nuclear reactions, the main purpose is to establish more stable nucleus. Alright, so what is the binding energy? The formal definition of the binding energy is the energy that is required in order to separate a nucleus into its separate nucleons. So if I have a nucleus that is very tightly bound together, me as a person, I have to do work, or not necessarily me, but something has to do work on this nucleus in order to separate these into its separate nucleons. So separate the protons separate the protons and the neutrons into So separate them individually. So once we separate each of them individually, the total amount of work done, that is equal to the binding energy of the nucleus. So therefore, the total binding energy would increase as the nucleus size increases. This is because there's going to be more and more protons and neutrons, and therefore it will require more work, more binding energy in order to split these protons and neutrons into their individual protons and neutrons. Alright, so likewise, the binding energy can also be defined as the energy released when nucleons are joined together to form a nucleus. So when nucleons are joined together, so when I have my protons and my neutrons, I'm going to join them together. The strong nuclear force is going to bind them tightly together, and some of these energy is going to be released. Because of the mass energy equivalence theory, the mass of the nucleus is actually going to be less than the mass of its separate nucleons. So the mass of the separate nucleons, that's the protons and the neutrons individually, will actually be larger than the mass of the final nucleus. Because once the protons and neutrons bind together, some of that energy is lost. Some of that energy is released, or another word for that is liberated. Some of the energy is liberated. Therefore, the final mass of the nucleus is actually less than the mass of the individual protons and neutrons. This is called the mass defect, okay, the mass defect of a nucleus, and this can be used to calculate the total binding energy of a nucleus. And that is your Einstein's formula, that is the E equals to mc squared, okay, that can be used to find the binding energy of the nucleus. Okay, however, that doesn't necessarily mean that large nuclei are more stable. It is the binding energy per nucleon, so the amount of binding energy per nucleon, so the amount of work I need to do to separate the nucleus into its individual protons and neutrons. So the per nucleon, it actually depends on the stability of the nucleus. And likewise, when I separate, when I do work to separate the nucleus into a separate nucleon, the work I do, the energy I do, the work is actually transferred into the system. Therefore, the mass of the separate nucleons will actually be bigger than the mass of the nucleus. So that's another way to explain it. Binding energy per nucleon. So the binding energy per nucleon is the determining factor of the stability of the nucleus. Although the binding energy increases with nucleus size, like I said, more nucleons, therefore more work needs to be done. The binding energy per nucleon actually begins to decrease after iron, element 56. Sorry, it's actually meant to say element 26 on the periodic table. My mistake there. Okay, so nucleon begins to decrease after iron. So after iron, as the nucleus gets bigger, the binding energy actually increases because there's more nucleons. However, the binding energy per nucleon begins to decrease. So therefore, the stability actually begins to trend downwards. So because when there's a large nuclear size, this actually increases the tendency of the nucleus to undergo a decay. So that could be a beta decay, alpha decay, or gamma radiation. We'll talk about that in part 2. So here we have a graph of the binding energy per nucleon. This is the y-axis is in mega electron volts. 1 mega electron volt is equal to 1.6 times 10 to the power of negative 13 joules. So as we can see here, very small nuclei are very unstable, as well as the bigger nuclei, the stability begins to decrease. As we can see here, the peak of this graph is at iron. So iron actually has the largest binding energy per nucleon, therefore it is considered the most stable nuclei. So as seen in the graph, the BEPN, so that's just the abbreviation for binding energy per nucleon. It's very small for small nuclei that have low stability. The most stable nucleus is iron 56. Iron is actually element 26 on the periodic table, but any element heavier than iron will undergo fission. 56 is actually the mass number of iron. Okay, that's the atomic number of iron. That's the position on the periodic table is actually 26. So any element heavier than iron will undergo fission, where large nuclei decay into smaller nuclei. Again, this is to become more stable. Okay. So nucleons in the nucleus. So we know that there are both protons and neutrons in the nucleus. The atomic number, that's sometimes abbreviated as Z, that determines the number of protons, and hence it is equal to the charge in the nucleus, because we know that the charge of the neutrons is 0, but the charge of the protons is positive 1. Therefore, the number of protons is equal to the charge on the nucleus. The mass number is also known as the nucleon number, so mass number, nucleon number. However, it is the amount of nucleons in the nucleus. So that's the amount of protons plus the number of neutrons in the nucleus. To represent elements in the nuclear equation, the following model is present. So we have X is representing our element, so it's an abbreviation. Therefore, if we said iron will actually be Fe, that's its abbreviation. Therefore, X in this case would be Fe. N is the nucleon number, so that's the number of protons plus the neutrons. So that's also the mass number. Z is the atomic number, and that's the number of protons in the element. Alright, mass defect. So when separate nucleons join together to form a nucleus, some energy is released, and due to mass energy equivalence, the energy liberated results in a decrease in mass of the nucleus, and this is known as the mass defect. This can actually be used to calculate the binding energy and hence the binding energy per nucleon of a specific element. So Einstein's famous formula E equals to mc squared can help us find the binding energy from the mass defect or vice versa. Here is a quick example. So calculate the binding energy per nucleon of an iron 56 atom. So 56 is the mass number. So here is the here's iron. We have mass number is 56, atomic number is 26, and here is the data we need. So our mass of a proton, I've told you, is 1.67262 times 10 to the power of negative 27 kilograms. Mass of the neutron is equal to 1.67493 times 10 to the power of that should say negative 27 kilograms, so 1.67493 times 10 to the power negative 27 kilograms. And mass of the iron nucleus is 92.85847 times 10 to the power negative 27 kilograms. Alright, so when we're doing this nuclear reaction standard, it's very important that all our decimal places are being rounded consistently at a very large amount of decimal places. We have to be very precise in the standard. So as we can see here, mass of proton over starter is given to 5 decimal places. So your final answer should theoretically also be in the 5 decimal places. Okay. So give a go at this question. Calculate the binding energy per nucleon of an iron 56 atom. Okay, so pause the video, give this question a go, and when you're done, keep watching the video to find out the answer. Alright, so how do we start this question, okay? So we know that the mass defect is simply equal to a difference in mass of its individual nucleons and the mass of the nucleus, okay? So we know that there's actually 26 protons in iron. We know that because the atomic number is given to us as 26. 26 is the atomic number that's equal to the number of protons. Therefore, we also know that the number of neutrons is actually equal to 30. There are 30 neutrons in the Fe nucleus. This is because the mass number is 56, and therefore, because there's 26 protons, 56 minus 26, that will give us our 30 neutrons. So therefore, we're going to add the masses of our individual nucleons. That's our first step. So mass of nucleons we have as M. I'm going to say it's mass of nucleons, Mn. That's equal to 26 times the mass of the proton plus 56 minus 26, which is 30. 30 times the mass of a neutron. That should give us the final mass that's 93.73602 times 10 to the power of negative 27 kilograms. Now we're going to find the difference between the mass of the nucleons and the mass of the iron nucleus. So therefore, the mass defect, we know, is actually equal to the difference in the mass, which is actually 8.77550 times 10 to the power of negative 28 kilograms. So now we're going to find the total binding energy for the iron 56 atom. To find the total binding energy, we need to use Einstein's formula. That's E equals to mv squared. Okay, sorry, what am I saying? So that's equal to E equals to mc squared. Okay, so we're going to say that binding energy and binding energy per nucleon. So we're going to say our binding energy is E equals to mc squared. That's going to give us the answer of 7.89795 times 10 to the power of negative 11 joules. That's the total amount of binding energy for the iron 56 atom. However, the question is asking us to find the binding energy per nucleon. So the binding energy per nucleon is simply will be the total binding energy divided by the total number of nucleons in the atom. In this case, we have 56 nucleons. Therefore, our binding energy per nucleon is our total binding energy divided by 56. And that should give us our final answer of 1.41035 times 10 to the power of negative 12 joules. And that's our final answer. Alright, so nuclear fission, okay? So nuclear fission is when a larger nucleus decays into two or more smaller, lighter nuclei in order to become more stable. So that's a key word. Bigger nuclei we saw in the graph above, it had, after iron 56 nucleus, the stability began to decrease. So we see these very big nuclei. So we know that because they are very big, we know that the strong nuclear force I was talking in slide 2, that is only acting at very small distances. So when there's a very big nuclei, some of the protons and neutrons are at a further distance, so therefore the strong nuclear force will be weaker. Therefore, sometimes the electrostatic repulsion will sometimes lead to a decay. Okay, so that can lead to a bigger nuclei decaying into two or more smaller nuclei, and this is to produce more stable nucleus. Okay. In the nuclear fission, a large amount of energy is released in the form of kinetic energy and gamma radiation in some cases. So form of kinetic energy, so basically if we have a larger nuclei, it decays into smaller nuclei, then this is going to be released in kinetic energy. So during fission, the mass decreases due to the energy release. Hence, the total mass of the products is less than the total mass of the reactants, and once again, that's due to the mass-energy equivalence. Since the products have a lower mass, they have a lower energy, meaning they are more stable. they have a higher binding energy per nucleon. So that's a keyword. Whenever the question is asking you to refer to stability, you always have to link that back to higher binding energy per nucleon. Okay, that's very key. So higher binding energy per nucleon means more stable. Okay, not total binding energy. That is wrong. It's binding energy per nucleon. And so here's an example of fission. So here we see that a bigger nuclei is actually decaying into the barium and the krypton nuclei. In this case, energy is released. Okay, so this is an example, a very popular example of fission reaction, fission decay or fission reaction. Okay. Alright, so nuclear fusion, so that's actually the exact opposite of nuclear fission. So in this case, it's actually two smaller nuclei formed a heavier nucleus. So remember, linking it back to our graph, we saw that the smaller nuclei, especially the very small ones like hydrogen, helium, they all have the very low binding energy per nucleon. Okay, in fact, hydrogen actually has no binding energy. The reason that hydrogen does not have any binding energy is because it only has one proton. Because hydrogen only has one proton, the definition of the binding energy is the amount of energy that is required to separate the nucleons, from the nucleus. Since it's only one proton, this has actually already been technically, it's already been separated. So therefore, this actually does not have a binding energy. So we know that the smaller nuclei have a very low stability. So therefore, nuclear fusion will cause two smaller nuclei to form into a heavier nucleus. Again, you can link this back to fission by saying that the purpose is the same because they want to create a more stable nucleus. Alright, so in order for a fusion to occur, the two nuclei must collide at very high speeds. And when I say very high speeds, that means very high temperature is needed in order to excite these nucleus in order to make them move at very high speeds. Okay, so high speed linking it to high temperature. So this is to overcome the electrostatic repulsion of the two nuclei. So when we have the two nuclei, where is that electrostatic repulsion? So that is electrostatic repulsion needs to be overcome in order for the nuclei to fuse together. So we know that there's a strong nuclear force. Okay, that's a strong nuclear force. It's only active at very small distances. Therefore, we need to force the two nuclei into this very small distance in order for the strong nuclear force to take hold and take control to fuse the two nucleus together. In order to overcome this electrostatic repulsion, we need a very high collision speed and therefore a very high temperature. So therefore, work is therefore done against the electrostatic repulsion. So work is done against the electrostatic repulsion to bring the nuclei together in order to form in order to fuse together to make the heavier nucleus. Right, so like fission, a large amount of energy is liberated from the reaction. The products have a lower energy than the reactants, hence again it's becoming more stable. So here's a very common example of a fusion. So in this case, we have a hydrogen and I cannot pronounce this very well, but hydrogen and a deuterium, and that produces our helium and our gamma radiation. So in this case, we have a fusion reaction. Alright, so fusion versus fission in terms of energy, okay? So 3 bullet points we need to remember. Fusion is releasing more energy per nucleon than fission. So in terms of per nucleon, fusion gives us more energy. So fission occurs with larger atoms. We know that fission occurs when a large nucleus decays into two smaller nucleus. Hence, they have a higher energy release per atom. So because the atoms are bigger, obviously the energy they release per atom is going to be bigger than fusion, and that's because fusion has very small nuclei compared to the fission. There are more light nuclei in 1 gram or 1 kilogram, 1 ton, whatever the unit is. So there's more light nuclei in 1 gram than 1 heavy nuclei. Hence, fusion releases more energy per kilogram. So those are the 3 bullet points. So the question might ask you that for example, compare fusion and fission in terms of its energy release per atom. For example, that might be an example question, and then you would explain that fission occurs with larger atoms, therefore it has a higher energy release per atom. So those are some questions that could come in the examination. So mass energy conservation in nuclear reactions. Mass energy conservation in nuclear reactions states that the mass energy of the products is equal to the mass energy of the reactant. So in this case, instead of having conservation of mass by itself and conservation of energy by itself, mass and energy are equivalent. Therefore, we're going to have our mass energy conservation. So in this case, this is the formula we need to know. So the total mass of the reactants times C squared, so that's equal to the mass of the product times C squared plus E, because we know that energy is released in fission and fusion. Okay, so energy is released. And therefore, the left-hand side will be equivalent to the right-hand side in this case. So here is an example. Show that the energy liberated is 5.5069 mega electron volts as a gamma photon in this case. We have our previous example, we had our hydrogen, I cannot pronounce. Okay, so hydrogen, deuterium, it becomes our helium and gamma photon, gamma radiation. So we want to show that the energy liberated is 5.5069 mega electron volts as a gamma photon. So here's the information we need to know. So we have our mass of the neutron, mass of hydrogen, nucleus, or just proton really. So mass of the deuterium, and mass of helium-3. Okay, so using these values, I want you to show that the energy liberated is 5.5069 mega electron volts. So give this question a go, and when you're finished, keep watching the video to find out the answer. Alright, I hope you gave that question a try. And in this case, okay, so first thing we've got to do is we've got to find out our total mass of our reactants. The total mass of our reactants would be the mass of the hydrogen or the mass of the proton plus the mass of the deuterium nucleus. So therefore, we know that these masses are going to add them together, and we're going to times it by C squared. And that is the left-hand side. That's the reactants. That's the mass energy of the reactants, and that's equal to the mass energy of the products, which in this case would be helium-3 times helium-3 times C squared. The mass of helium-3 nucleus times C squared plus whatever energy is liberated. So in this case, once we rearrange to find out E, we'll find that E equals to 8.811 times 10 to the power of negative 13 joules. We know that 1 mega electron volt is equal to 1.6 times 10 to the power of negative 13 joules. Therefore, we'll find that the total amount of energy released in terms of mega electron volts is equal to 5.5069 mega electron volts, and that is our final answer. Alright, so writing nuclear equations. So when writing nuclear equations, the amount of charge is conserved as well as the total number of nucleons. So here's the basic reaction for a fission reaction. So in this case, we have our N, which could be represented as our bigger nucleus that has a certain amount of nucleons, X, and a certain amount of protons, Y, okay? And that's going to decay, that's going to become A nucleus plus C nucleus. And each of these is going to have its mass number, which is total number of nucleons, total number of protons. And C, element C will also have its total number of nucleons and total number of protons. So therefore, in this case, X represents the nuclear number of the original atom, Y represents the atomic number. So the conservation of charge and nucleons means that the total nucleons of A and C must add to give X. So we have our A plus D equals to X, and therefore B plus E equals to Y. Okay, so total number of nucleons the same, and total number of the charge is the same. Okay, so the protons is the same. So B plus E equals to Y, A plus D equals to X. So here are a few examples. So here's an example question. So I want you to find out the value of X and Y and write out this equation of this alpha decay. Alright, so in this case, you should have got the following answer here. So once again, that's just conservation of total number of nucleons and conservation of charge. Example 2. We have this equation. Okay, so remember N represents a neutron. Okay, so N, the small n, is actually representing a neutron, so keep that in mind. And I want you to find the value of X, Y, and B, and X, Y, A, and B. As you should have got the following as your answer. So just double check that you've got this, got the same answer. So question 3, we have I want you to find out the missing element. Okay, so we have our nitrogen plus one neutron, and it becomes our carbon plus something else. Okay. Right, you should find that our last one's actually just a hydrogen, okay? So just check if you've got the exact same answer. So last question we have here is, I want you to find the value of x and y. So easy question here. Right, so we should have got our following as our answer. So once again, just check with these practice questions that you have the exact same answer for your exact same answers as shown here. Right, and that's it for this part 1 video. Okay, I hope you enjoyed watching this video, and if you did, please drop a like, please subscribe to my channel, and I hope to see you on the next one. Thank you, bye.